Alright, continuing in this series of videos, whatever, watching some physics lectures and commenting on what might be better alternative conceptual descriptions of the reality or how the thing really works. At least at minimum better language than things like wave-particle duality and whatnot. Anyway, let's get to it.
Okay, we're going to talk about light. Light is an electromagnetic phenomenon. And already in the 16th century...
Okay, so he calls it an electromagnetic phenomenon. They've declared that. They haven't demonstrated that with any kind of, real facts. It doesn't do anything electrical or magnetic. You can't move it with magnetism. It's just, no evidence that it really is some sort of mechanism moving through some sort of thing called a magnetic field. The irony is they also believe light is bent by gravity, which isn't supposed to be electro or magnetic at all. And, so it doesn't make much sense.
Way before Maxwell, a lot of studies were done of the interaction of light with water and with glass. And the kind of experiments that were done follows. Say this is air, I call that medium 1, and this is water.
A lot of these experiments done by Newton. I don't know why he didn't just say that, but yes, Newton.
Call that medium 2, and I have a light beam that strikes this surface. Light comes in like so, and I define this angle as the angle of incidence, and I call that theta 1. This is the normal to the surface. We call that the angle of incidence. I will see now that some of that light is reflected with an L as in lion, and some of that light goes into the water. We call that refracted with an R as in Richard, and this angle we'll call theta 2.
Alright, so the sum part probably is never really talked about it, but it's really proportional to the angle. So the steeper you make the angle, the bigger that theta 1 is as an angle off the normal, the more of the light will reflect and the less of the light that gets refracted. And at a certain point, you'll get no refraction and it'll be all reflection. And it's just not, it's a simple enough idea, it just isn't made clear when they're describing these things.
And it was a Dutchman, Willebord Snellius, who in the 17th century,
again with this Dutchman crap,
found 3 rules that govern the relation between these 3 light beams. The first one is that this beam, and this beam are in one plane. As you see, that is my plane of the blackboard. The second thing that he found, that this angle, theta 3, which is called the...
Kind of an obvious thing. So what he's saying is the light doesn't go in 2 directions. That is, it's not for some dopey reason. It can only move in the direction of its, I mean, quite obviously you could move the plane anywhere you want to, and then it looks like it's 3-dimensional. But, it can't move in 2 directions at the same time, so it obviously can't be in any but one plane.
Angle of refraction is the same as the angle of incidence. That was known before him, of course. And then the third one, which is the most surprising one, which is called after him, which is called Snell's law, although his name was Snellius, is that the sine of theta 1 divided by the sine of theta 2, if we go from air to water, then that ratio is about 1.3. If you go from air...
So what he did was, that Newton didn't do, was recognize that each material has a different index of refraction.
To glass, it's a little higher. It's like 1.5 or so. He introduced the idea of index of refraction, which I will call N, as in Nancy, index of refraction. For vacuum, the index of refraction per definition is 1, but it's very closely the same in air. We always treat it as 1 in air. And in water, the index of refraction is approximately 1.3, And in glass, depending upon what...
So I think that's a little low, actually. So you're just talking about whether it's 30 or 40% difference in terms of both speed and how much it bends.
kind of glass you have, it's about 1.5. And so we can now amend this law, Snell's law, by writing here n2 divided by n1. N1 being the index of refraction of the medium where you are, your incident beam, that's why I put a 1 here, and 2 being the index of refraction of the medium where you're traveling to. You refracted into this medium. And so you see indeed that since water is 1.3 and air is 1, that this ratio for air to water is 1.3. And this is called Snell's law. And it is immediately obvious that if you go from air to water, or you go from air to glass, that angle theta 2 is always smaller than the angle theta 1, because this number is larger than 1. But if you go from water to air, then the situation is reversed. And that's what I want to address now. That's actually quite interesting. So now,
So the difference is where the angle bends towards the norm, towards the straight line, or bends away from it. And so if you're going to a lighter medium, it goes away. If it goes towards a heavier medium, it goes towards the normal.
Medium 1 is now water.
I guess you should say even the surface. So if it's a heavier medium, you go away from the surface. If it's a lighter medium, you go towards the surface.
And my medium 2 is now air. And so now I go from here to here. And so here I have my angle of incidence, theta 1. And here I have my angle of reflection, that is this theta 3. And now here I have my angle theta 2. So if I write down now Snell's law, then I get the sine of theta 1 divided by the sine of theta 2 is now n2 divided by n1, but n2 is 1, divided by 1.3 if we go from water to air. And what is so special here is that theta 2 can obviously never be larger than 90 degrees. And so if you substitute in here theta 2 is 90 degrees, then you will find that theta 1 then is about 50 degrees. And if you apply this equation and you substitute for theta 1 an angle larger than 50 degrees, you're going to find the sine of theta 2 being larger than 1, which is nonsense. It cannot happen. And so nature ignores Snell's law, and nature says, sorry, I can't do it. And what nature now does, if the angle of theta 1 is too large, in this case with water larger than 50 degrees, this is not there anymore, and all the light is now being reflected off that surface. And we call that total reflection.
So it's basically saying the refraction disappears, and that's what's causing the reflection to increase. So as you steepen the angle, you increase the reflection, and it's a consequence of the fact that less of the light can refract. So it's an inability to refract that's causing the extra reflection. Probably.
Total reflection. So total reflection happens when theta 1 is larger than a certain critical angle.
So again, this idea that any of this stuff actually reflects is something that's need to be pointed out, that we call it a reflection because that's what it looks like to us. But in all probability, all of the photons are actually absorbed into the atoms and they're re-emitted. So they're U-turning or they're doing some other process to be changed in their direction. So it's not like there's anything like a pure reflection.
And the sine of that critical angle, for which I write CR, is n2 divided by n1, but there is a condition, and the condition is that n1 must be larger than n2. If that's not the case, then there is not total reflection. And total reflection is actually very interesting. It has a practical application, which I will discuss with you shortly. But I first want to do a demonstration in which I want to show this to you. I have here water, and here is air. And I have a laser beam which I can shine in, and I can change this angle theta 1 and slowly increase it and you will see that when I approach the 50 degrees, first of all, you will see that theta 2 increases, and then when I approach the critical angle and exceed it, then we have 100% reflection. So let me first turn on the laser so that the
So what else should be seen is that the amount of light getting refracted diminishes. It doesn't just stop.
there's a little bit of light, and I'm going to show it to you there for those of you who are not sitting very close. And that means I have to set the light situation. Okay, so there you see the light coming in just the way we had it on the blackboard. This is the way it comes in water. This is the refracted part, and this is the one that is refracted into the air. So that is this one here. And now I'm going to increase that angle. When I touch the table, the water will start to wiggle a little, and you will probably see that.
So the top one disappears, apparently.
So I'm going to, I decrease. I'm going to increase that angle. Look how I'm increasing it. Look, that theta 2 is getting larger. It's going to approach the 90 degrees. I increase theta 1. I increase theta 1. Look at
Getting
theta
dimmer
2.
and dimmer.
Almost 90 degrees. I'm very close to the critical angle now. I'm almost at it right now. And now all the light is being reflected. 100% reflection. A remarkable phenomenon. And this has...
More interesting would have been analyzing also how much of the light is going inside the glass and reflecting internally inside the glass, reflecting off one layer and the bottom layer.
Practical applications. And we're going to show you some of these practical applications too. The most important practical application is fiber optics.
You could argue that the first layer doesn't pay much attention to any glass to air problem, and so it's only refracting through the glass itself, and then it's the second layer where you have the transition between glass and air, and where you have a deflection because of the material difference between those atoms. The real key point being that none of this works unless the light is transferred through atoms. It's transmitted through the atoms. It doesn't travel through the medium. It has to travel through the atoms. The atoms communicate the light from one surface to another surface. It doesn't just shoot to the other surface.
If I have a fiber and it is properly designed, so this is a fiber, and some light comes in here, and it hits here, so this is, say, some plastic or glass, and this is air. If this angle of incidence is larger than the critical angle, 100% reflected. And so nothing comes out in the air, 100% reflected. Here, again, the critical angle is exceeded, and so 100% is reflected, and you can go through this whole thing for miles on end. You can put even knots in there. As long as you never exceed the critical angle, that light will propagate, and there will never be any loss of light. That's why people are very much interested in it. You can transport even images, as I will show you, through fiber optics. I have here a fiber optics, which has 4,000 fibers in it, 50 microns in diameter each. And we have a laser beam here, and the laser light will come out. I'll show you the laser light shortly there, and it doesn't matter what I do with the fibers. I can even go 180 degrees and shine them there. As long as inside the fiber, I always...
Kind of demonstrating that its light is transmitted. Obviously, it's being U-turned, in this mechanical way. So you're taking force going one way and reversing it. But the only way you can do that, it has to do it through the transmission medium that's really bending it a little bit at a time through a process.
Exceed the critical angle.
I mean, it's a bunch of momentum transfers, essentially. I mean, a force goes in one way, and a force comes out the opposite way, and then you have to have a lot of equal but opposite reactions inside of the fiber to create that circumstance.
I don't want the television anymore, so we can turn this off. And let's here have the laser light. There it is. Here you see the laser light. Okay, now look at this bundle that I have here.
All right, so this was made in 2007 or something, so obviously this would have been a lot more fascinating back then. I mean, it's kind of old news.
I'm turning it into an absurd snake. almost like an S. All the light still comes out. So it goes all the way through. I'm going to turn it 180 degrees around and turn it to the wall there. There it is. So there's an amazing phenomenon that this light doesn't get out in the air. It stays inside the fiber. And that's the idea behind fiber optics. I have another application of fiber optics right here, which is very similar. You can send an image through fiber optics. This is my fiber optics now. Thousands of small fibers. And I send a message in here. This side, an image. Could be a person, could be a text. And here we have a TV camera. And we can watch that image. On this side of the fiber appears that image. And this television camera will be able to see that image. And let's see whether we can show you that message. Okay, have to do something here again. I think you're going to, there it is. So you actually can see the individual fibers. You see them? How interesting? Each one, these are individual fibers. And their diameter is probably not much more than 50 or 100 microns. Let's see what message there is for you. Oh man, exam 3. You don't want to hear about that, do you? Well, it depends on what the message says. Problem? No. No. Problem 1. Problem 1. The figure, below. Oh, I must have, that's the wrong message. I couldn't possibly meant to give you away the exam, of course. So I apologize for that I showed you the wrong message. But at least it demonstrated to you that you can send an image through fiber optics, even secret messages. Newton had an interesting explanation for
secret messages. Anyway, so now he's going to talk about Newton and what he understood and what Huygens understood, and that the back and forth there. And I mean, this is really important just because it just demonstrates, that there's these little subtle things that physics turns on, and they're not really what they think they are. They think a coincidence is something, and then when there is something that is something, they think it's a coincidence. It's that kind of thing. They don't recognize when something's a real effect and when something's, a false indicator.
Snell's law. Newton was the man of planets. He was the man of particles, masses, accelerations, F equals ma. And so his explanation came with particles. He says light are particles. So if this is the surface between, let's say, air and water.
Again, Newton didn't know anything really about atomic structure, protons, electrons, all of this complexity of an atom. So of course his understanding is going to be rudimentary, and they're really taking advantage of that in the sense that they're saying, well, this is what a particle does, when we know now that a particle is a lot more complicated than just saying it just bounces off of something, because it does get absorbed by electrons and all this kind of stuff.
Newton argued as follows. If light comes in, it has a certain speed, v1, and therefore it has a horizontal component, and it has a certain vertical component.
So again, let's understand. So Newton already was already comfortable with the idea that there's a speed limit to light. That there's a speed element to it. Where people just assume that he presumed everything to be instantaneous. Well, clearly he wasn't presuming that.
And he says if this light ends up in water, at the moment that it reaches the surface, it gets an acceleration perpendicular to the surface. Why? He didn't tell us. But he said it gets an acceleration.
Right, and these people make a lot of statements, and the why they don't tell us. They don't know what a photon is. They don't explain any of these interactions in any kind of complex manner, any kind of atomic or nuclear manner. It's, they're just talking about some sort of, it does this, and this is what it does, and you just accept it. All of quantum mechanics is made out of that. Just accept it. Don't think about why.
Perpendicular to the surface. In other words, this horizontal component does not change. That remains what it was. But this component changes. This becomes substantially larger, depending upon the index of refraction, of course. And so the new velocity is now in this direction. And so you see that indeed the angle theta 1 is larger than the angle theta 2.
Yeah, so Newton was just trying to find an explanation for what they understood to be the facts, and it's just not a very it's not right. It's not a good explanation. They should have just left it alone.
But Snell's law immediately follows from this. The sine of theta 1, this angle is theta 1. So this angle is theta 1. So that's this velocity divided by this vector. And the sine of theta 2 is this velocity divided by this vector. But these two velocities are the same. And so you immediately find that this ratio is v2 divided by v1. A great victory for Mr. Newton. Except there was one problem, maybe, that it means that v2 is larger than v1. And so Newton argued that the speed of light in water is larger than the speed of light in air. And in glass, of course, it would be even larger.
Right, and he's also basing this on, they did sound experiments also, so they had some indication that sound traveled faster in water than it travels in air. Faster in dense objects than in light objects. So that's part of their intuition. Yeah, it's a reasonable guess, but wrong. And now they're going to say, well, because Newton was wrong, okay, and Huygens' guess is, accurate, that somehow these two guesses weren't both ignorant. And that neither one of them is right. But instead they've decided to choose. Badly.
Now there was a Dutchman, and the name of Dutchman was Christian Huygens. Huygens. And this gentleman suggested that perhaps light are not particles, that they are waves. And this guy...
Waves of what? Waves in what? Waves traveling in corpuscle fashion. How? How do they do that? How do the waves travel in a straight line without spreading?
Came up with a genius idea, which we now know as...
See, just genius nonsense, really. I mean, it's just another bad guess.
Huygens principle, at least you call it Huygens principle. But we don't call it Huygens principle. You see, this sound, UY, is pronounced in Dutch as ui. None of you can say ui unless you're Dutch. To make it worse, this sound you don't have either in English. That's a None of you can say unless you're Dutch.
Nobody would want to. Nobody would want to put in their name. Yeah, we're not that stupid. Yeah. We don't have instruments like violins that play sounds like Yeah, we don't bother with that because it sounds like shit.
Let alone that you can say the combination Huygens. Anyone who comes forward to me after this lecture and who knows how to pronounce the word Huygens has to be Dutch. I will be kind to you and call it today Huygens principle. So Huygens came with the following idea. Here is a source of electromagnetic waves. And these electromagnetic waves propagate out in a spherical way. Not unreasonable.
Totally unreasonable. Because we know they're photons, individual photons. So individual photons have to have insane amounts of momentum to be going in everywhere at this, every direction at the same time. Yes, they'd have to be insanely, an insane amount of invisible energy.
And so you even see here the wave crests. And so he defined the surface at the leading part of the wave, where all points are in phase. He called that the wave front. So this is the wave front. And he now postulated that each point of the wave front individually oscillates at the same frequency as the source and produces spherical waves. We call them secondary waves, often also called wavelets.
Yes, magical wavelets, an infinite number of them to boot. And this is, like I said, this is what they cling to, merely because he guessed light was slower in glass or water. And because he guessed correctly, he's right. And it's a nonsense theory.
And that the envelope of the wave fronts of these secondary waves is now the new wave front. So it works as follows. Each point that you can choose as many as you want to, starts to oscillate at the same frequency as the source and produces on its own spherical waves. There they go. And the new wave front
somehow producing energy in the wrong direction, not accounted for in any way. How does it waste energy shooting stuff in the wrong direction? The photon is actually shooting stuff in the wrong direction.
Is then here. And this is called Huygens' principle. Because he doesn't give any explanation of why these points do.
Yes, no explanation. So obviously we would put in the same category as Newton's guess and just say, they're nice guesses, but they're just guesses and they're not very good.
Do that. He hypothesized that. And this principle can explain Snell's law in a very easy way. I want you to read up on that in your book. And you will see that it is very easy to explain Snell's law with this principle, except that now you will conclude that the sine of theta 1 divided by the sine of theta 2 is V1 divided by V2. And therefore, Huygens predicted that the speed of light in water is lower than the speed of light in air, whereas Newton predicted that the speed of light in water would be higher than the speed of light in air. So the question now was, who was right? Are light particles or are they waves? Well, the wave-particle idea of light has been a very long-standing issue in physics. And I will show you, I think next week, or maybe after the exam, how Young in 1801 conclusively demonstrated.
So, conclusively demonstrated with an experiment Newton had already done 150 years earlier. Just completely unremarkable experiment in many ways. And just because it had two slits and made it very convenient for comparison to water waves, everybody fell for it and just ignored the fact that the same thing happens with a single slit and it doesn't happen in water waves, and the two experiments don't match. And so they just cherry-picked the evidence clearly, and that's the history of science, is cherry-picking and becoming writing guesses into the book of fact.
That light are waves. So it looked like Huygens was going to be the winner. On the other hand, I showed you last lecture that light can behave like particles, photons, bullets, tomatoes, radiation pressure. That's particles. The whole thing. The whole ball of wax. And so maybe Newton was right. Maybe they are particles.
So he says, nail in the coffin. Then he says, maybe. It's just a complete breakdown in all kinds of rational language. There's just no rational conversation here. This wave-particle duality is nonsense. It's just silly to say they're both. It is either one or the other. And they ought to get to the business of actually proving it one way or the other.
Well, they're both right. There are times that you can actually interpret what you see best by assuming they're waves, and that there are times that is much...
And again, you shouldn't have to be doing all this assuming. Again, it's a fundamental principle in the sense of it's fundamental. It's elemental. And if you don't get this elemental stuff right, the rest of your building is garbage. This is like leveling the foundation. I mean, if you don't have a level foundation, you're just going to get yourself into trouble. And so physics really should find this to be critically important to resolve these questions decisively. And instead they just propagandize.
Better to assume that they are particles, like in the case of the radiation pressure. But of course the key question now is, who was right in terms of the speed of light? Is the light going faster in water than Newton was right, or is the light going slower in water than Huygens was right? Needless to say that the Dutchman was right. The speed of light in water is lower than the speed of light in air.
And it's perfectly understandable in terms of you understand that the light's being transmitted. Something is opaque or something is transparent. It's not like the mass of a glass. If this pen was made out of glass, it was actually way more than this plastic pen. Yet this plastic pen is blocking all the light, and the glass transmits all the light. So clearly it's not about light just hitting stuff. It's about the fact that it has to be transmitted. The material has to be in a certain arrangement where the light goes through it, and it goes through it reliably. Comes out the other end in some coherency to how it went in.
When we derived the speed of light in vacuum, we used Maxwell's equations.
Yeah, you didn't really use Maxwell's equations. You used two constants that had already been created for the very purpose of matching the speed of light, because the equations don't work if you don't have the accurate speed for the speed of light. So your constants were engineered essentially to predict the speed of light because they had to.
And they allowed us to conclude that the speed of light, much to everyone's surprise, depends on epsilon 0 and mu 0 in a very simple way. I will call it for now V.
Let's understand, epsilon 0 and mu 0 were not measured quantities. They didn't go out and measure the permittivity of space. They didn't measure whatever the other one is. Those things were never measured. So they're not real values. They're just constants. And they're constants engineered for the purpose, okay, of making the equations more accurate. So clearly they were predicting the speed of light by having constants that match the speed of light.
That was 1 over the square root of epsilon 0 mu 0, and we call that C. If you had used Maxwell's equations as they are valid in materials, in dielectrics, and also in materials that have magnetic properties, then it would be exactly the same derivation, but you would have seen a kappa here, the dielectric constant, and you would have seen here the magnetic permeability. Kappa, if you're not in air, but in glass and water, it's always larger than 1. So you see in front of you that the speed of light and water is lower than the speed of light in air. This can also be written as C divided by the square root of kappa divided by kappa m, and we would nowadays simply write that as C divided by n. So the index of refraction is really the square root of the product of the dielectric constant and the magnetic permeability.
And again, the bottom line is the speed changes because the material is transferring. It's going through more atoms to get through the material to be transmitted. More atoms means each process consumes some of the speed of the light because the light's not traveling in a straight line to get from point A to point B. The force is not moving the speed of light. The entire process of transferring the force from atom to atom to atom to atom has in it elements of movement of electrons, which is slower than the speed of light, and that the electrons slowing the force down, essentially. So you're just really saying how many electrons did the force have to go through to get from point A to point B, and the number of electrons will tell you how much slower the light is, because that's the amount of force that was moving electrons rather than force that was traveling the speed of light. You just have to understand that it's like the speed of light is going the speed of light down a sidewalk, let's say, and then it has to, because it can't go across a river or something, it has to get on a bus, go across the bridge, across the river, and then it goes back on the sidewalk and goes the speed of light again. So it's a force, then it's going really slow in a bus, and then it's by force again, and then it goes back on the bus, and then it goes in force again, and then it's back on a bus. So the light itself didn't slow down. It's just that the process of moving the force from one place to another has bits in it where the force isn't moving its speed. It's having to push a big, it's like you running 50 miles an hour, and then somebody says you have to push a snowball, every quarter mile. You have to roll a snowball, and it's going to slow you down. Then you go fast, and then you roll a snowball. I mean, however you want to metaphor it. But you have to understand that the more snowballs you have to roll, the longer it's going to take you to make the trip.
Now kappa and kappa of m are very strong functions of frequency, and that's not so surprising, because at very high frequency the intrinsic electric and magnetic dipoles, which are being aligned by the alternating external fields, cannot follow quickly enough. A field wants to drive them in this direction, and it wants to drive them back and forward and back, and there's just not enough time to do that.
Right, so they just end up being in an average position going like this instead of swinging.
And so you expect that at high frequencies, the values for kappa are lower than at low frequencies, which is exactly what you see. In the case of kappa m, that's only important when you deal with ferromagnetic materials.
So it doesn't slow it down as much because at high frequencies, everything's just doing this instead of doing the full motion thing, that kind of thing.
Because with paramagnetic and diamagnetic materials, kappa m is always 1 anyhow, or very close to 1. I have chosen water as an example to show you the dependence of kappa on the frequency. This is on the web, so you can download it and make yourself a copy.
So red light, blue light, different colors lights will move at different amounts of change in their speed. I think this is what it'll come down to, I believe.
And so if you look here, this is for water, then you see there at low frequencies, at 0 hertz, and even at radio frequencies, at 100 megahertz, this is 100 megahertz, this is radio waves. Notice that the dielectric constant in water is about 80, and at visible light, these are the frequencies of visible light, it's way lower. We just discussed that. The oscillations go too fast. The electric dipoles can't follow it. And so the index of refraction then for radio waves at 100 megahertz is roughly 9, and so the speed of those waves in water is 9 times lower than the speed of light in air. We call it speed of light, but it's the speed, of course, of the radio waves then. And in the case of visible light, you see that visible light in water, the speed is only 1.3 times lower than what it would be in air, or of course in vacuum.
Lower. I thought it was... Yeah, right, it's lower, right. Sound is higher, so that's the non-intuitive part. The sound travels faster in water, the light travels slower. Is transmitted slower.
The frequency effect is very noticeable. If you take red light and blue light, they have different frequencies, and therefore the index of refraction is different for red light and blue light. If I take water, the numbers I'm going to give you are for water, then the index of refraction for red light in water is 1.331, but the index of refraction for blue light in water is 1.343. And we're going to use these numbers.
Not a huge difference, but a difference nonetheless. So blue is a little bit slower, little bit slower. Anyway, so it's probably a good time to, so I will, and such. But yes, it's all interesting. This refraction surfaces. This is where physics has, dropped the ball in my opinion, because what happens on surfaces, transitions between mediums, this is hugely important, and I don't think they've recognized they need to go a bit deeper to find out the real mechanism. And it's not some magical infinite wave producing Huygens nonsense. So anyway, till the next time and such.